Hello, everyone. My name is Peng, and today I want to give a presentation of our video CVF unified video editing with temporism. It is accepted at CVPR 26 with a highlight, and um and this is the highlight is accepted with 2.5% of all the CVPR submissions. And first, I want to short introduction of our video CVF. It is unified video editing with temporal reasoner. And you can see first, why we need reasoning before the editing, like this one. The first, the left is that naive sampling learning methods. It just input the noise-free source video and the fully noise edit video and temporal concatenate. But we want to remove the man with green shade on right. It is not right. It at the left man. But our video swap, it first predicts the reading frame. It is reading where to edit and then predict the corresponding editing results. So it is right. And our video swap can edit video through the C reasoning and editing process. It can reasoning where is the blue cut and then remove it. So we are very accurate. And also we can reasoning where is the right man and then remove it. We can also do something like extrapolation. This is a Sora video, and we only train on 33 frames, but we can generalize to 144 frames. Yeah, that is the martial video editing results. We can also do something like unified video editing. The first is that instance level object removal, like remove the left woman, and also remove the background girls, like the girls wear blue sweater, and the red woman, yeah, the young black red woman. We can also do something like objectation, like add a small something on the left, and follow the man's the action, and add a white woman pinpoint to the black blow, and add a woman on the left mimic white man's action. And we can also do something like object swap. This is instance level object swap. We can swap only the man's clothes to the black jacket, as well as the middle woman's jacket to the navy blue blazer. And we can also do something like swap the red hoodie to the denim jacket. And we can also do something like very complex local style transfer, like swap the rabbit to the cobra colors. Like also, yeah, like doing something like text rendering, swap the school logo to the hospital logo, just re-rendering the text with only generated model. Yeah. Okay, so continually, I will show you why we are doing unified video editing with temporal reasoner. The first is that there's some expert models like we know they are database models and feed the mask to the video generation model and yielding some precise and localized results. It is accurate but require additional mask, and it can only do one task for one model. Yeah, like this is a video painter Tencent SIGGRAPH 1025 papers, and it can in this video it can remove the middleman, but it requires the mask sequence, and yeah, and video painter can only do video removal. And for the width, it also requires mask to specify the location and only support for the object swap, like it needs the Orbing's ID and the layout mask, so it can do the object swap. But there's also another trend in our community. We can call them as the unified tempering learning methods. They can unify multiple video editing tasks like object addition, removal, swap, and style transfer. But they are exhibit very weak accuracy, especially in cases like need multi-instance recognition in very complex world scenario. And this is one Unix demo. Unix actually it requires masks, and it is a caption based. But the cell phones work like ICVE, trained on 100 million video, source video, and doing something like 150,000 video editing data supervised by tuning. It can just the naive temporal can learning, and it just encode the text embedding and source a noise-free video and fully noise active and temporal candidate and execute the in-kind learning methods. It is mask-free, but it is not accurate, and it cannot do spatial understanding like left and right. So we ask a question is that, can we maintain the precision of expert models and unification of in-kind learning methods without such kind of mask dependency? So like what I previously showed the left demo, this is ICV's result. It can not remove the man on the right. It removes the man on the left. But our video web it learning about where is the right man with green shirt. It reasoning like the green mask frames, and then add the corresponding results. So we call our video editing is like chain of frames editing, like first predict the reasoning frame, then predict editing frame. Why we design this? That is because what I said, there's a accuracy and a unification trade-off. Expert models, they are accurate but mask dependent, but unifying methods, they are mask free but less price. And also there's a very important problem in video editing. We can call that the video editing length extrapolation problem. The naive temporal inclination method, the temporal index is from 0 to f minus 1, and then can get another video from f to double f. And it cannot editing the video in the beyond the training lines, like we just input on 100 frames, but training on 33 frames. It will overfit to a static mapping, like from 0 to the train length f. So it will hinder the very important extrapolation problem. So and continue, I also want to introduce our task. The first is that multi-instance object remove, like remove the left man, the background girls, and also like something object addition, like also multi-instance level object swap, like swap the left man's where, and also something like multi-instance local style, like only pans the right bottle, the green chili bottle to purple, and the text rendering, something like this. And this is the framework of our video set. We are a unified framework that enables the generative models to reasoning over the video content before editing. And we enforcing a C reason and the procedure, predict the reading tokens before generating the target video tokens. And our source video token, they are not free. And the reading tokens corresponding to the reading phrase, it is in the RGB level. And also the noise latent tokens are corresponding to the add video results. And in this way, we first predict reasoning, then predict the editing. We will have three benefits. The first is that we enforcing video generating models, diffusion models, to predict the reading tokens for the editing real. And we do not need the user provide mask. Our model will predict mask for the editing rate, and therefore we have the interpretability of video editing, since that we can know whether the model predict the right area, that is like the left side, and also whether it is the problem of instruction to textual alignment. And in this way, we can also enhance the editing accuracy. And for the text encoder design, we are doing something like temporal dispatch prompt. And the template is that a video sequence showing three parts. The first is original scene, and then go on the left side, and then finally the same thing, but blah blah blah. And for the drop design, we just set the source video to from 1 to f and the zeroing to 0, and the output video from 1 to f. And why we designed this? That is because for naive temporal learning methods, if you just temporal concatenates from 0 to f minus 1 and from f to double f minus 1, you can only learn a fixed mapping from 0 to f. Like 33 south, 33 add, you can only learn a mapping from 0 to 33, right? And another directly methods is that you set the cells from 0 to 33 and add the add the video from 0 to 33, and also the raining from to 0. But you can see the left figure. That figure is that the raining frames did have some raining format. It is like mask on the raining frames. But this kind of raining frames linked to that results. That is because the temporal lobe index, they are collision. So we set the raining frames temporal index to 0 and set the source video and edit video to the frames to the temporal index 1. And therefore we isolate the rain tokens and prevents artifact leakage from the reasoning to the editor, and we maintain the length generalization. Like there is also a mapping from 1 to F to edit 1 to F, source 1 to F. Yeah, and you can see this is a rope alignment qualitative ablation. Like the naive temporal inconnex, it can only edit like 33 frames, but our rope alignment can edit more than training length, like 81 frames. And also you can see what I previously showed. This is the Sora multi-shot video, and we only train on 33 but generalized to 141. Yeah. That is also not the upper bound of our methods. Continually, I will show you like this one. This one is a 10 seconds. It's a 40 seconds video. It's a 50 second video with 10 IPS, and we only train. We import this video using our VideoCoF, and our model is only trained on 33 frames, so it have a 16 times less generalization of our VideoCoF. Yeah. Yeah, and this is editing result due to time limitation. I won't display for. And most surprisingly, we can edit the multi-shot video. We only train on single shot 33 frames. And you can see this is left is south, right is our edit. Edit it to a blue handful in an generated video. This video is also generated, and you can see we can keep the identity consistent across multi-shot. The shot, the camera transition, and the identity is not continuous across all shots. It have multiple character, but our video set can only edit the woman character. Yeah, and it's very consistent. So we actually learn very robust lens generalization ability. So our rope alignment strategy, and this is our data creation pipeline. Actually, we have a very big video pool, like 200 2 million videos, and we filtered it using chain wheel 27 billion models, and we're using it to filter some multi-instance data. And we use some multi-instance data. We have such kind of multi-instance data, and we're using Groundino to ground each instance. And then we separate each instance, and we then extract each instance next to construct some addition or remove data. We're using special expert models like minimax remove. Like we given this mask, we just remove the woman. And also, we're dilating the masks, and we're using width to construct some swap or local style transfer data. And after get this data, we're using the DOP score like beauty score and VS score. This is edit score to filter some goat editing triplet pairs. And we're using chainwheel 27B to construct some the generated instruction. Yeah. And finally, we only have, like you can see, 50,000 video editing data. It's a very small column. And the editing results is also fancy. We can do something like multi-instance object remove, like only remove the right girls, and remove the computer, and remove the background doggy. And we can also do something like object addition, and not that the edited chimpanzee follows the camera, and also the stalker is follows the man's kicking actions, and we can also like adding a woman mimic right man's motion, like very, very strong spatial understanding and action understanding ability. And this is a result of multi-instance object swap results. So we can just swap the left man's clothes to the black jacket and swap the left woman's clothes to a blue t-shirt. And we can also do something like spatial reasoning, like multi-instance level local style, like swap the right apple's color to purple and swap the left's bird's color to blue. Yeah, that is something like spatial reasoning, then editing. Yeah. And quantitatively, we compared with in situ with scenario task with MSV and Lucy Edit. We always get the best results. We get a very high instruction following score and far exceeding the previous score, and the success ratio is also nearly 20% points higher than the run-up. And we only tuning on 50,000, but SAV is pre-training on 1 million video and fine-tuning on 150,000 samples. So we are data efficiency. This validates the data efficiency of our chain frames paradigm. And we also show something for the qualitative comparison. We want to remove the right man, but ICV or Lucy Edit, they are not execute right. And for object addition, like we can add a small girl just behind the washing machine, but step form add the girl just in front of it. Yeah, with destruct the background, and also for multi-instance object swap, like video swap can swap the old man to the young woman and change the teacher to blue jeans. But you can see SCVE just also replace the white woman and with destruct the whole background. Yeah. And for multi-instance local style transfer, you can see we want to paint the larger larger cup writer. Obviously, they can reasoning which cup is the larger, but SAVE can paint the cup and the both. And as with it destructs it destroy the background. Yeah. And this is ablation of our reasoning frames. Not that the right frame is the predicted result. It's generated. It is generated by our VideoCoF model. You can see the reasoning frames is very accurate, so we can add the dough to the to the newly baked bread, and also remove like the blue card. And we also ablation of the chain frame slope designs, like it is whether we should temporary slope index from 0 to double f minus 1 or 0 f minus 1 0 0 minus 0 to f minus 1. Finally, such kind of from 1 to f is the most right design. And for the ablation of our rope alignment, you can see if we set south video from 0 to f, and it will collision, and the running frame will leak to the editor video. But and the motion is not alignment. You can see finally the man leaks close, but 0 to f it cannot, since it have something kind of motion collision. Yeah, and our rope alignment strategy is right. That is from 1 to f. And also we can doing something like length extrapolation, more than the training length, and you can see 0 to double f minus 1 it decreases after training length. And we also did something like the learning format. For the generative model, the learning frames should be in the RGB pixel level, and when the learning format should be black background or the red foreground or just gray foreground. And finally, we validated that with the transparency from 0 to 750%, the gradually increased transparency is the best choice of your rendering format with gray as a color. Yeah, and this is the rendering frames ablation and tree patch prompt ablation. And you can see in this video that the middle is video editing tree patch template results, and this is a direct instructional results, like just makes the t-shirt saluting. And our methods can keep the texture while add the color of the t-shirt, but directly instruction editing fields. And also we choose that the which kind of learning frames is most suitable, since we know the temporal conversion of VAE in video generative model is 4. And finally, we experiment shows that 4 learning frames is the better results. And that's all. Thank you very much.